Hi, this is Hassan Korani. In this video, we are going to continue our chapter about functions for grade 10. The objectives in this part are construct the table of variations of a function, find the extremum point or points of a function, certain function. Well, at the beginning, table of variations of a function. We'll do this by an example. Well, usually whenever you are asked about construction of table of variations of a function, you will be given the curve of the function. So we have to construct the table of variations from the curve, from the graph of a certain function. The table of variations is a table. It has usually two rows, x values and one for the y values. F of x, as you know, represents the ordinates or the y values of a function. Well, as you see, we have given this simple curve of a certain function. As you see, it shows increasing in the first stage and decreasing at the second stage. And we have to recognize these red points, these critical points. And we usually, it's helpful to draw this vertical line that separates between the first stage and the second stage, where it increasing and where it decreasing. So as you see, since the function here it is increasing, so we draw an arrow, an increasing arrow here in the table. Then it is increasing in the second stage, so we draw a decreasing arrow. Here, as you see, we have a glowing point. This point is of coordinates -2, -3. We place -2, -3 here. Be careful, -2 represents the abscissa and -3 represents the ordinate. Here we have another glowing point at the end of the first stage, where it stops increasing here. So this point is of coordinates 2, 5, so we place 2 with x values in the x rows and 5 in the y rows. As you see, here we have the last point, which is whose coordinates are 4, 3. So similarly, we place them in the correct way, 4 with the x values and 3 with the y values. By this way, we have constructed or set up the table of variations of this function. This is the table of variation of that function. It increases and decreasing. Here we have an arrow showing the increasing stage and the decreasing stage after that. This point is called the maximum point, as you see. Okay, let's see another example. Given the curve of a function f in the adjacent figure, as you see, we have a somehow complicated to curve. It shows increasing, decreasing, increasing again, then decreasing again. We usually place these critical points. This helps to construct correctly the table of variations of this function, separating these vertical lines that help us to construct the table of variations. The table of variations is, as you see, here we have the first stage increasing, so we place an increasing arrow, decreasing with decreasing arrow in the table. We keep a gap here in order to put the values, the y values later. Then increasing, as you see, we have an increasing stage here, increasing of the function. So we place an increasing arrow, again decreasing with decreasing arrow. Here we have a glowing point, starting point, whose coordinates are -4, -5, as you see from the figure. So here we place, put the x value, the abscissa here, and the ordinate here, over at the beginning of the arrow, not here. So then after that, we see the second point at the end, whose coordinates are -1, 4. We place -1 here and 4 there. The next glowing point here, this point whose coordinates are 1, 0. Here we have 1, 0 again, and that point whose coordinates are 2, 1, and we place 2, 1 correctly here, there. And the last point is of coordinates 4, minus 3, and here we have 4, minus 3. By this way, take care about the placing of the y values correctly in the table to get the correct answer for the table of variations of the function. Let's see now the maximum point, that means the maximum or minimum of a function. By doing this, seeing this GeoGebra activity, as you will see, let's consider this curve of a certain function. As you see, now the question is where we have the highest point of this function, the highest value of this function, y values. As you see, A in fact stands for the highest, or the that has the highest, greatest y value. So we say that we have an absolute maximum here. Why it's absolute, which means the total maximum, the highest value of the y value of the function. Here we have a maximum, but we call it the local maximum. Locally here we have a maximum point. It is greater than the previous point and the points after it, so we call it local maximum, where the function stops increasing and starts decreasing. So we have a local maximum and the absolute maximum, which is the highest point. Sometimes we may have as you will see, here we have, let's say, this point. This point is local, yes, since the function stops increasing and starts decreasing, but at the same time this point constitutes the absolute maximum. At the same time, it's the absolute maximum and the local and a local maximum of this function. Okay, let's see another case where we have an absolute minimum. As you see, absolute minimum is the lowest point, which is here, the absolute minimum of this curve, of this function, where we have the lowest value of y, of ordinate or y values. And as you see here, we have a local minimum y since the function stops decreasing and starts increasing over here. And again, we may have this function sometimes, in some cases, it may constitute the absolute minimum at the same time. As you see here, we have D is a local minimum and the absolute minimum, since no point below it. Okay, so these are the absolute and the local maximum, and these are the absolute minimum and the local minimum. Okay, let's see the definition by words. Given a function f defined over its domain I, an absolute maximum f admits at x equal a an absolute maximum if f of x less than or equal to f of a for any x belongs to I, so all the y values below it, so it constitutes the absolute maximum of a function, of the function f. Local or relative, sometimes we call it relative maximum. F admits a local maximum at x0 belongs to I if f stops increasing and starts decreasing. As you see, if we have this shape in a certain portion or certain part of the function, so we say that we have at this point a local maximum. Stops increasing, starts decreasing, so we have a local maximum directly. The absolute minimum f admits at x equal b an absolute minimum if f of x greater than or equal to f of b for any x belongs to I, so all the y values are greater than or equal to this value, y value, so this point is the absolute minimum. The local or relative minimum f admits a local minimum at x0 belongs to I if f stops decreasing and starts increasing. As you see, if you see this shape in a certain part of a curve of a function, given curve of a function, so we say that this point constitute the local or the relative minimum of a certain function. We will end this part with this application with GeoGebra that shows a maximum with another point of view. As you see, we have a triangle and we have a variable rectangle here, sure, with variable area. The question is where, for which value of x here we have a maximum value of y, maximum value of the area of this rectangle. Again, the question is what is the maximum area of rectangle ODMC if we change x c or xm. As you see, we can see this by drawing in another orthonormal system. Let's see this. Let's say that this point represents the area of the rectangle in terms of x. As you will see here, the area increasing as we move the rectangle, this point on this side, and the area increases till value 5, where it achieves its maximum value at x equal 2. As you see, we can see it, and then it decreases again since the rectangle loses its area as we go downward till it reaches 0 area, as you see, when dm is confounded with the horizontal axis, the x-axis. Okay, so the maximum area is this, where x equal 2, the area of this rectangle is 5. Before it, the area is less than 5. After it, the area is less than 5 also. Okay, this is it for in this part. Thank you for watching, and see you in the next part.